Hello again, my dear friends, and welcome back. We're going to talk about queues one more time, and this is lesson number 14. Okay, just to remind you, last time we introduced the concept of queues, their presence in real practical life, and the concept of queues in computers. We have went through a bunch of applications where queues can be used in computers, and we started talking about the different functions that we use to manipulate queues. Okay, we introduced some of these functions in terms of prototype, and today we're going to continue on these functions and give some more prototypes on the basic functions that can be used. So that's the first thing we're going to talk about in this class, in this lesson. Basic operations on queues, that's a continuation basically to what we have covered so far. And then after that, we're going to talk about the implementation of queues. There are different ways of implementing queues, as we're going to see, and there are variations of these implementations. Okay, let's start. More on the prototypes. The function we want to talk about now is clear the queue. Well, as with the stacks, in some situations, I would like to flush the content of the queues, to throw all entries in the queue and start fresh with no entries in my queue. Basically, that's the function which is going to perform this operation. And this function, which we call clear queue, is going to be of type void, no return value. However, it's going to take as an input a pointer to our queue, a pointer to our structure. So here's my queue. Okay, basically I have some entries already in here, but for some reason I want to clear them out. Front was pointing here, rear was pointing here. All right, and there is of course a pointer to the data structure comprising the queue, which we call small q. All right. So the assumptions that we're going to make for this function as a precondition is that the queue already exists, has been already created, and it has some entries obviously in there. The outcome of this as a postcondition is that all entries inside the queue have been removed and the queue is empty now. So as a result, I'm going to throw away all of these entries, adjust front and rear so that they point to an empty location. And as a result of this, the queue is going to be empty, no entries in there. However, the structure of the queue is going to stay the same. I'm not going to destroy the structure representing the queue, but basically no entries inside the queue after I call this function, after I return from the call, as a matter of fact. Okay, another function is to give the queue size. And again, in many situations, I would like to know exactly how many people are waiting in the line for service. Okay? And this is definitely different from the actual size, the maximum size the queue can take. Let's say the maximum size set for the queue is to accommodate 1,000 entries. However, at the moment, I only have like 100 entries. All right? So I would like this function to give me the exact number of entries that are physically now inside my queue. Okay, the name of the function is queue size, and it's going to return to me an integer value. This integer represents the number of entries, okay, regardless of the size of each of the entries. And this is obvious, I assume. So again, the only argument it's going to take, the only parameter I'm going to pass is just a pointer to the structure of the queue. So star q or asterisk q. The precondition is that the queue here is already created and has been initialized. Okay, and it could have as many entries ranging from 0, no entry, up to whatever maximum allowable, as we have reserved for it when we defined our data structure. After return, this function is going to return the number of entries in the queue as a return value for the function. All right. another function called QFront. Remember when we talked about stack top or top of stack entry, to where we wanted just to make a copy of the entry on top of the queue of the stack without removing it. It's the same thing in here. I would like to retrieve in some entry of the same type as entries inside the queue. I want to put a copy of whatever I have at the front of the queue. So I'm not going to remove that entry from the queue again. It's not like service, but rather it's just a copy. So basically, if this is my queue, and I already have few items inside it, and that's where front is pointing. Of course, this is rare as usual. Okay, and then the outcome of this function is that I would like to take whatever data inside this and place it in here. Make a copy of it in item. Don't remove it. Don't alter this. Keep this item standing in front of the queue. It's just make a copy of the contents of this entry in the entry here called item. So again, this function, which is called QFront, is going to take basically two parameters. The second parameter here is actually the queue structure, a pointer to the queue, and another item parameter called item. And as a matter of fact, because I'm going to change the content of this, because it's going to take whatever inside this entry as a copy, okay, that's why I'm passing it as pointer. And this entry, this parameter, is of type QEntry, same as the type we have in here, in these items, as big, as large as it is. The return value of this function is of type void, because that's not what I want actually, that's not my focus. My focus is on this item, okay? Because this item is going to be now filled with the data from the queue. The precondition for this is that the queue, named queue, already exists and it's not empty. And that's why before we run this, we call this function, we have to run the queue empty function to make sure that our queue is not empty. Otherwise, we're attempting to copy from nothing, from an empty queue, and in that case, I have an underflow. The post condition, the item at the front of the queue, this one, is going to be copied into this location called item. However, without removing this item physically from the queue. So it's going to stay inside the queue. However, we're going to make a copy of it and place it in the memory pointed by item. So queue remains unchanged as a result of this. The last function we want to talk about is to traverse a queue. And again, traversing the queue is the same as in concept to traversing a stack, to where I would like to visit every entry inside my queue, all right, and perform certain operation on that. Go change the grades in there, go change the salary, go change the content, whatever kind of content in there. Basically manipulate these the entries in there. I could do a major operation by, let's say, adding all the salaries because I'm calculating the budget I need to put. So I'm gonna visit every entry in this, read something from there, or write something to that particular item within the entry, and so forth. This is called traversing or visiting the queue. So basically, to traverse the queue, I will need to have a pointer to the queue, and again this is letter Q and not letter S. Seems we're having lots of troubles in here because actually these functions are similar to the stack which we covered. So this is Q rather than S, just to be consistent with our notation so far. So this is a pointer to my queue, and then the function itself, which we called visit. and this visit function is of any type, which could have any return value, right? And it takes as an input the queue, the entries inside it. So I will read basically every entry in here, pass it to this visit function. This visit function is going to perform some operation on the entry and return it back. So I'm not taking out any data from the queue. I'm not adding any new entries in the queue, but rather I'm manipulating the entries already existing inside the queue. Okay? So based on that, then the precondition for this is that the queue, small q, is already created and it has some entries. It's not empty, otherwise why to bother visiting it? And as a post condition, the function visit the items has been invoked, has been performed on every and each entry in the queue, beginning from the entry at the top, pointed by front, and up to the very last entry, pointed by rear. So basically, to do that, I'm not going to touch front, I'm not going to touch rear, I'm not going to change them in a sense, but rather, visit will have some sort of a local variable of type integer, same as front and rear, an index to the entries in here, and basically it's going to start from front and I'm going to increment it along the way. Each time I will read the content of the entry, do whatever I want to do with that entry, and then advance that pointer to the next entry and so forth till I get to rear. So basically, we're going to implement this later on, but basically it will have some sort of a loop like this for current, and that's my local variable, equals to front, current, less than or equal to rear. So basically, current plus plus. Basically, I'm going through every one of these, and in between, I will do what I would like to do on the entries. Okay? We have seen a similar function like this when we were talking about stacks, so it's pretty much a repetition. The only difference is that in the way this front and rear are actually treated when we were talking about queue as compared to top, the only one pointer that points to the stack. I think we have talked about this, but it doesn't hurt if we go back and talk about it again. QEmpty, this is basically a function which checks whether the empty we're handling is full or is empty or not, if it has any entries or doesn't have any entry at all. So basically, as we said earlier, it's going to be of type Boolean. This is the name of it, and it takes the queue we're having in hand. And basically, there are no preconditions for this. The only precondition is that this actually queue already exists and it has been initialized. As a result, this function is going to tell me a yes if the queue is empty, no entries in there. And basically, in that case, front and rear are going to be equal. They're pointing to the same location, and basically that location is nothing. It's a location, but no valid entry in there. That's what I mean. And otherwise, if I have any entries, it's going to return a 0, a false, indicating no, there are some entries already in this queue. I think we have talked about this, but it doesn't hurt, as I said, if we go through it again. These functions, whatever we covered today and whatever we covered in the last lesson, are going to be implemented actually in a sort of C code later. But before we do that, let's look at the way we're going to implement the structure of the queue. Remember that we used arrays to represent stacks. Okay, and we have created them either using static structures, fixed size of the array, or we have used the malloc dynamic allocation, the malloc and free functions to create them along the way. Well, pretty much the same in here. we're going to be implementing stacks basically using arrays. However, we have to be a little bit careful in here. And let's look at the way we're going to implement the queues using the arrays. Okay, with stacks, as with stacks, we can implement queues using arrays. No difference, basically. However, we must keep track of front and rear. To where in stacks, we had to care about just one pointer called top, which always point to the last entry in the stack, because anyway, if you're gonna add beside that, when you're gonna pop from the stack, you're gonna pop from that same location. So we're pointing to the same location in additions and deletions. However, in the case of queues, we're adding at one end and we're removing from the other end. And for that, we have to have two pointers always, one pointing to the top of the line, and one points to the rear of the end of the line. And that's where I serve, and that's where I add new entries. Okay, the question is how to keep track of these two different indices since they are pointing to two different things, and some of the functions work on this and some other functions work on this pointer. Okay, the different examples that we have, the different scenarios. The natural solution, and that's the first method. Well, according to the solution, the most natural, the first way of thinking about the problem is to keep front always in the first place of the array, like this. And we have to be a little bit awake in here and careful. Here's my queue. It's some sort of an array. Okay? And that's where my front is. And what we're saying in here, keep this pointer always pointing to the first entry in your array. Never change it. Never remove it. Well, let's see. And now, the first comer, the first customer is going to come all the way and sit here. Fine. The second person, the second customer comes here. This is an append. Third customer is going to come here. Okay, now it's time to serve. Well, this person is going to go out of this queue. What to do? Let's see. An entry is simply appended by increasing the counter showing the rear. So at the very beginning, rear was here because I don't have any entries. And now I have one entry, so I'm going to advance this to here. A new entry comes, so I'm going to move it here, and so forth. So rear keeps moving as new customers are coming to the queue, as I'm appending to the queue. However, I will always keep front here. So in case of appending, I don't have any problem at all. Well, as if there is a problem with the front. Yes, let's see. Well, to serve or to dequeue an entry, all the remaining entries need to be moved one position forward up the queue to fill in the vacancy. Because when I serve this person, now here's the picture of the queue after I serve the first person. This one has already been served, so it's empty now. However, I have an entry here and I have an entry here. Front is still pointing here. As I said, I'm not gonna move it. All right? So this is an empty location. Well, if I want to keep front this way, then what I have to do is something like this. I'm gonna move this entry forward so it sits in the first place. And then this is going to be empty. I'm going to move this one to this place. And that's the natural way. We call it the natural way because that's the way it goes in the queue when you're in the bank or when you're at the airport buying your ticket or at the supermarket and so forth. So people are standing in line, okay? The first person is going to be served. Once it's served, everybody is going to move one step forward, okay? And the person who's serving those people actually, who's pointing to front, all right, is always sitting in his place. He doesn't move. He or she doesn't move. Okay? So who moves actually are the people in line rather than the pointer front himself. Well, is there a problem with that? I don't see any problem. That's what we do in the airport, in the bank, in the supermarket. Well, there is a problem with that. And the problem with that is that the solution is very expensive because actually you don't know what you're moving to fill in this vacancy here. Actually, in the case of people standing in line, you're going to move yourself. No big deal. One step forward and we're done. Easy. The cashier person is going to stay sitting on his chair waiting for the customers to come to him. Well, what if the customers we're having in here are actually carrying heavy luggage and they can't move forward simply? Okay, then that's a problem. I cannot really, with each time I serve a person, to ask those people to carry all the luggage they have and move forward one step. It's going to be disastrous for them. So the other alternative would be something else actually. You go to them instead of asking them to come to you. But the natural solution is this, is that if I have a vacancy in here, then I have to fill it and move forward this entry and move forward the second entry and so forth for the rest of the entries we're having in here. Well, in real practice, let's not talk about luggage and human customers. Actually, these entries that we're having in our queue could be huge structures. I don't know, maybe 1 kilobyte of data, 10 kilobytes of data, a huge amount of information about those entries. Okay, so if I'm gonna move physically each of these records forward one position, each time I serve one of the records, that's gonna be a huge, massive amount of data transfer with every single service. And that's why we say that this solution is very expensive. So here's a picture of this way of solving this problem. At the very beginning, I don't have anything, and I'm appending now. The entry goes here, front and rear, pointing to this entry. No problem. We don't have problems with the append, as a matter of fact. And no entry comes in, fine. Place it in the second available space, and now adjust rear to point to it. A third entry that goes back here, and I'm adjusting rear accordingly, and so forth. So there's no problem actually with the append function in here. However, when it comes to the serve, okay, I'm ready to serve this first entry in here. So this is going to go out of my queue, and then after that, I'm going to end up with a vacancy in here. And that's where I need to physically move this entry, the orange one step forward. The green one needs to be moved forward to sit in here, and the light blue one is going to move to here. And if this amount of data is huge actually, and it depends upon how many actual records we have in here, we could end up with a huge amount of data transfers. Okay, but at the very end, I will have something like this. I'm happy with it. Front is sitting on his chair waiting for the customers to come to him, but along the road, a massive amount of data has been transferred from one location to another. And that's why the solution is very, very expensive. Are there any alternatives? Yes, there are. Let's think of this, what we call linear implementation solution. We're going to use two indices, 2 pointers, rather than just one, which is the rear, back and forth, and front was always fixed. Why to keep it fixed? Let's move it, okay? And that apparently will solve our problem, at least for now. One index is to keep track of front, and I will change that as things move on, and one index to keep track of rear. So basically, I'm going to have something like this. Here's my queue, okay? And I'm going to assume that I already have customers like this. So here's my front, and here's my rear. Nice. Now when I serve this and it goes out of the queue, I'm going to move front and make it up here rather than here. And in that way, I will move to the data, and this requires the movement of a pointer, and that's just 4 bytes worth of data, regardless of the size of the actual entry in here. All right? So no matter what the size of the entry is, pointers are always 4 bytes long, and so moving them is not costly at all. So this basically then, apparently at least, solves the problem I was talking about when I was talking about the natural solution. The advantage, no need to move entries anymore. I move to the entries. The pointers will move to where the actual data is located within my queue. Excellent. Well, then according to the solution, to append, basically increase or increment when I append at the very end, I increment the rear pointer by 1 because the new entry is going to come and sit here, right? And then I'm going to increment the rear counter so that it goes and points here. Put the entry at the new position in the queue, and you're done. That's when you append. Okay? So basically, a new entry comes, rear was here. I need to move this to point a new empty location, and I will take the new entry, place it in here. That's the append. Easy. Let's see the serve. To serve, take the entry from the position at front. Let's say front is already here. So I'm going to serve this person now. Okay? So this is going to be out of the queue. And then front is going to be, after that, adjusted and point to here. So front is going to be here, pointing to this entry now, and these 2 entries are vacant. So take the entry from the position at the front and increase the front index by 1 so that it points to the next entry. Excellent and perfect. Not much of data is actually being moved. I'm only moving pointers, and as I said, it's just worth of 4 bytes each time I need to move any of these pointers. Here's a picture of it. I'm in the middle of the operation. Okay, I've already made lots of serves. Already those people who were here already served, so they're gone. And each time I service any of those customers in here, the front was advanced by 1. And now it's pointing to this entry. Rear is pointing to the last entry, filled entry I have in here. Okay? So anytime I would like to append, I will move this to here and place the new customer in this location. Anytime I need to serve, I will take this out of the queue, and then I will increment this down to here. So I'm always incrementing, as a matter of fact. Each time I serve, front gets incremented. Each time I append, rear gets incremented. Do we ever decrement in this case? I'm afraid we don't. And well, that is a big problem. Because as we move on with this, okay, lots of appends, then lots of services along the road. We're moving downward in the data structure comprising the queue. What about those entries at the beginning of the queue? They're empty now, right? Will I ever go back and utilize these entries? I already served all of those people, okay? And I have customers here. Fine. Here's front. Excellent. Not much of data transfer. What about these locations here? Am I going to be able at a later time to put people in here? No, you don't insert in here. You don't append in here. When you append, we append here, right? And I'm going to be servicing from here. So these locations, I'm afraid, are going to be sort of wasted. They're not going to be used again. So both front and rear indices are increased, but they're never decreased, according to the solution, at least according to what we have said so far. Well, as a result, the queue moves down the array, right? as we service people. And the storage space at the beginning, this one, is actually discarded and never used again. And this is a problem. So yes, we thought we made it. We thought we found the best solution because we're not moving much of data, but apparently we're not doing well because we're losing a whole bunch of space at the beginning of the array once we have several services. Let's see that in an example on the screen. It's very similar to what we were talking in here. However, let's say I have a queue already, and then I append, then another append, I serve, append, serve, and so forth. Bunch of these consecutive operations in the order they come. Let's see how that's going to happen. I appended the first time, so the entry goes here. I append again, okay, I go here. Now front is pointing here, rear is pointing here. I serve, okay? Well, if I serve, the entry in here is going to go out of the queue, and I will have front adjusted so that it points here. So now in this situation, both front and rear are pointing to this entry. Well, I'm appending again. Append is going to go here, and rear is pointing to this entry now, front here. Several times of these appends and services, back and forth. Well, at the end of the day, I'm going to have my front, because I had so many services along the road, I served so many people, then these locations are going to be wasted storage, and I can never go back to them. Because according to the proposed solution, we don't decrement front or rear. We always increment them. When we do append, we increment rear, and when we serve, we increment front. No decrements whatsoever. And that's a defect in the solution. So it's not the best solution on earth then. Well, we have to look for another way of doing it then, to utilize the space in a better way. Because otherwise, I'm going to run out of space very fast. It depends upon the number of customers I'm having, regardless of the size of the storage. Okay? The third solution is actually what's so-called circular arrays. What are circular arrays? Well, circular arrays, we use the concept of the modulo function. And I will look graphically at my array as if it's a circle, something like this. Okay, so as if I, with the paper in here, instead of looking at my structure as a flat structure like this, I turned it around like that, like a cylinder. Okay, and at the beginning, I will call this my beginning, the beginning of my structure, my array, and this is the end of the array. However, in a sense, these front and rear, they actually meet at some point. And I go around this. So I will go like that, appending if you like, and I'm servicing from here. Fine. When I reach this point, the very last entry, basically, this is entry number 0, and this is entry number n-1 in my array, actually. So typically, in the normal structure that we have for the array, no other entries come after this. You go beyond the scope of your array. However, in the concept of circular arrays, when we use the function modulo, the one which comes right after this is actually this. So it's like if I'm wrapping around in this structure. If that is the case, then why worry about the space? Because once you end in here, you're going to go back here. So what you think was wasted in here is actually going to be utilized once you're through to the end, and you're going to go back and start filling in here. And this is the ultimate solution and the perfect solution for this case. So circular arrays are used to overcome the inefficient use of space. In concept, we simply think of an array as a circle rather than a straight line, a flat structure. In this way, as entries are added and removed from the queue, front will continuously keep following tail, actually. It's chasing tail or rear, what we called so far, around the array. Okay? And it circulates around. Let's look at the picture in a second. If that is the case, if I wrap around and front and rear keep chasing each other, one after the other, then I will not actually get to the end of my structure, because my structure always circulates and I always stay within the scope of my structure. So hence the queue will occupy different parts of the array. Yes, I could have these entries, these locations filled at a time. So I have front and rear sometime in here. But later on, as I append more and service more, I could have entries in here, and I will have my pointers here and there. So these pointers are going to keep circulating around this donut, if you like, and I will always have these two pointers pointing to the very first entry, which I will serve next, and to the very last entry, to where I'm going to add an entry after it, just in case I need to append. And in this case, I will never have an overflow unless, of course, the whole thing is filled. And then I'm going to have a full queue in that case, and I can't add any new entries. But overflow is, we can understand it, and we know when it happens, and we check for it anyway, and we don't take customers if my queue is full anyway. So that's not a restriction on the implementation method. Here's a picture of it. And instead of looking at it as a straight line kind of implementation, we're doing it in this fashion. So at any given time, I'm having again the two pointers, the one pointing to the first or to the front entry, one pointing to the rear. However, instead of wasting the space in here, I'm going to utilize it when I go to this kind of implementation, to where the first entry closes with the last entry in the array, in the structure itself. So actually, that's the first entry, second entry, third, 100, 10th, 10,000, whatever, and then at the very last entry, the one which comes after that is actually entry number 0. How to do that? Well, do you all know the modulo function? Let's say 10 modulo, or mod for short, that's the word used for it, 8. What does this equal to? Well, it says, what is the remainder of dividing 10 by 8? So I basically take 10 divided by 8, okay? And that equals to 1 with a remainder of 2, right? So the modulo is 2. So that means I went once around the entire structure, and in my second round, I took 2 positions. And let's do that here. Here's my array. 8 positions. This is position number 0, and I want to go to number 10, okay? And this is 1 up to 7, right? And after 7 comes 0 again. And then after 0 comes 1 again. So the 10 modulo 8 is actually 2. That means I go to this location. Okay? So after this position, I'm going to go back here, and then here, and then here, and so forth. So I keep circulating. So physically, I don't have a circular memory, but rather I have a flat memory. But when I use this modulo function, I'm going to be performing the operation on a circular structure rather than a flat structure. That's basically it. We're going to end here today, and next time we meet, we're going to implement these functions we talked about. Of course, you can always refer to the UNINETTUNO website. Click on the MidNetU project to see this material and more exercises and other supplementary material. Thank you very much for today, and I will see you later.